Hello everyone. My name is Alex. I have been testing open source software for the last 10 years. This is how to reach me if you like. And this is how I look. No, pretty close. Today I'm going to talk about mutants and zombies, but not the ones from the movie. Slightly different. And I have some code examples. So first let me get an idea. How many of you are familiar with Python, at least to some degree? Okay, good. And how many of you are familiar with Ruby? Okay, great. So don't worry, the examples are not very hard to understand. So let's take this piece of code. It's a simple class describing one model. In a Rails application, there's only one field that goes into the database. This is only one method, which is actually a really stupid method, just returns an uppercase string of that field. As you can see from this screenshot, this class has 100% code coverage. And the question that I'm asking myself as a tester, and the question that I expect everybody should be asking themselves here is my test suite good enough? And good enough in terms whenever there's some change in the software under test, is my test suite able to detect if this change will break something or the change goes undetected and possibly goes into production and something bad really happens. And mutation testing can help you answer this question. But first I need to explain what a mutation is. So a mutation is usually a very small change in the software which somehow changes the behavior of the software. Mutations can come from comparison operator and if statements. And if we take the example on the screen, it's the mutation is replacing the greater than operator with a less than operator. And if you apply this mutation to your code and read it, it becomes if age is less than 18, then buy beer. Now imagine that you are an online store and suddenly you start doing this, sell beer to small children, and this is not good. Then another possible source of mutations is constant values. You can replace these values with something else. And in this example, we replace true to false. And because it's very early in the morning yet, if we didn't have our coffees, we would be looking like this. Another possible source of mutations is loops. We may, for example, modify the loop condition. Or in this example, we may change break to continue, and we get an endless loop. And when you have an endless loop, this is what happens. So this is again an example from production, and all my examples are taken from production environments today. Well, not the beer one, but by definition, mutation testing is a technique, and also the tools for mutation testing. They modify your software under test. They don't modify your test suite. You keep the test suite separate. And for each mutant that is produced in your software under test, you execute the test suite again and again and again. And this gives you a pretty good idea at the end how good your test suite is. It can tell you places where you have tests, but they don't do a very good job of finding all possible things that may change. Or they can also tell you places where you have missing tests, but you already know this, because we use coverage. So mutation testing is really good for telling you where you need to make better tests. And the idea behind this is some of the mutations which you see and which the tools support try to mimic errors which developers may do while writing code. For example, +1, -1 errors, delete something by accident, and just commit this to source control, stuff like that. And other mutations which you may see, they are purely artificial, but somehow they help us validate the test conditions, the test environment which we run our tests within, and help us expose something that's missing. The algorithm for mutation testing is actually very simple. So we run 3 loops, one after the other. First one is we go through the all mutation operators that our tool in particular can support. These are stuff which the tool knows how to change with something else, regardless whatever that else may be. Then for each operator, we find the places in the source code where that operator is used and replace it with something else. Most operators and conditions can lead to only one another type of mutation, but sometimes you can produce different mutations for only one place in the code, like with the comparison operators. And then, of course, you execute the test suite. There are three simple rules to kill mutants, which you must remember. First, when you execute the test suite against the non-modified version of the program, everything should pass, and this is a hard requirement. You cannot go without it. If something fails, obviously, your software doesn't work or your test suite is broken and you need to take measures. And if you have flaky tests, and sometimes they pass, sometimes they fail, and you have no idea why this is, obviously your mutation results will also be unreliable, and you need to take measures to fix your flaky tests. The second rule is when you run the test suite against a mutant, that is a modified version of your program, you expect the result to be fail, and that's a good thing. When the test suite fails, then we say that the mutant was killed or the mutant died. And this means we had at least one assertion or one condition in the test suite which wasn't met, and the test suite failed. So that means at least we have one test which is able to detect this change and tell us, the software was modified. And the last thing is, which you don't want to happen, when you run your test suite against the mutant and the result is pass, this is a bad thing. Then we say we have a zombie, or that the mutant survived. And as you know from the movie, zombies are these things that go around and try to eat you. And now imagine you make some change in the code, run the test suite, it passes, but it doesn't really understand there's anything change. And now this change goes into production, and suddenly this becomes a bug and tries to eat you. So these are the three rules. Testing against the non-modified version should pass always. Testing against a mutant should fail. This is the way mutation test tools figure out when you kill the mutant. When something fails in the test suite, the tool says you kill the mutant. Okay, now let's play a little game. I am going to show you possible mutations, and because you all know about testing, you are going to tell me what test cases I need to write to kill the mutants. I am using the code from earlier, the one with the 100% coverage, and only take this method. See, this is a string variable, and we return the uppercase of the string variable. That's what it does. So very simple. First possible mutation is instead of returning the uppercase string, my method under test returns nil value. So what tests can you propose so I can kill this?
Obviously not new.
Yep. Yes, obviously not new. Yes, correct. So we execute the method under test and expect the result to obviously not be new. I'll go back. If we apply the mutation and run the test, the method will return new and the expectation will fail. Everything will fail and we kill the mutant. Okay, next possible mutation. Instead of returning the uppercase string, I'm returning self, because this method is part of the class and I have access to the self object, so I can do this. What test do I need here to kill this mutation? Okay, type string, correct. So I must be checking what the type of the return value is, and if I expect only string, then it must be only string and nothing else. Another possible mutation is instead of returning the uppercase, I just return the value of this variable as is. So how do I kill this? Okay. So I start with a value which is lowercase, and then I execute the method under test and expect this to be uppercase. And I use this with just a constant because it's easier for me.
Isn't this one enough for all those zombies?
No. So this one, for example, will kill the first and the second zombies. And here, if I start with new, okay, let me think. With the new mutation. Yeah, it might kill also the first one. So sometimes, yeah, one of the tests is enough to kill more mutants. But actually, this is the way I discovered them and I developed the test for them. And actually didn't go back to think whether or not I have some test which is not needed. And okay, so and the last example from the game is replacing this ampersand. This is the new safety navigation operator in Ruby, and I just replace it with a dot. So for the folks who don't work with Ruby, the new safety operator works this way. If the object on the left is new, then the result of this operator is new and nothing else is executed. And if the object on the left of the operator is not new, the execution continues to the right. And when we replace this with a dot, then if a language code is new, we just get a runtime exception because a new object doesn't have a method called upcase. That's the difference. So we do this mutation, and what tests do I need to kill this? Should what? Should not roll. Okay, how do you assert on that? Okay, well, at least I don't know how can I assert that there was no exception, but I can set this variable to new, execute the method under test, and if there is an exception, the test will fail anyway, so I don't have to assert there wasn't an exception, but I can assert that the result was new. So if the framework asserts whether an exception was not raised, then of course that's a valid answer, but I don't know how to do this with Ruby. Sorry? Oh, okay. It collides if you read it collides if you read the examples as is on the slides. What I haven't shown is that this variable has a non-new value by default. So that works then. But yeah, good catch. Now let's try and find some bugs with mutation testing. One bug that I was able to discover just by using mutation testing in a project, not actively looking for the bug, is this. So we have a class called network, which represents the networking settings on your Linux computer. And there's an attribute called self-device, which is the name of the network interface. And this method for equality is obviously wrong, as highlighted here, and we'll see why. So if self-device is none or an empty string, that piece of the Boolean expression is always evaluated to false, and the entire return value is always false. So it doesn't matter what's the other object you're comparing to, this method always returns false. And if self-device isn't none or is not an empty string, then which means it has some meaningful value in the software, this is evaluated to true, and the Boolean expression always depends on the second part. So, and that's actually the fix. Just remove this first part of the Boolean expression, and here we go. The reason this stayed undetected for, I guess, about 7 or 8 years is there wasn't a single test in the test suite which tried to test this equality method when some of the attribute was an empty string or was none. So they were always testing with some valid values, and this went undetected for many, many years. And also in the software under test, when you see normal conditions, this value is always it always has some value, so it doesn't return false or something bad happens. Another bug which I was able to find is, as shown, I have 2 classes. The second class inherits from the first one, and you see both classes have a parameter called speed limit in the init method, and both parameters have default values. Now this is perfectly valid Python code, so there's nothing wrong with the way it's written. I run this through mutation testing, and I get a surviving mutant. The reason here is this is a constant change. The tool for Python adds +1 to any integer constant, and to see what happens. And I immediately know the reason for this is that I don't have any test which creates an object from this class and asserts what the default value of these attributes should be. So I create my test like this, just create an object from the class under test and assert what the default value should be. And the test immediately fails, of course. And the reason for this is, if you look closely, you see that this parameter, I'm not sending that to the init method of the parent class, so it must go here after self. And when I'm not doing this, the parent class has its default value, so it uses 50 instead of 90. And that's why my test fails. And this is also very subtle. It stayed undetected for many, many years. And also the reason for not being detected is the attribute this value is assigned to is never used in the software under test. It was meant to be used by external clients of this software. The software under test in this case is a library, so it's used by other tools. And apparently, nobody bothered to check whether or not the default value is it should be. Another possible bug, very close to the previous one, is again I have two classes. The second class inherits from the first one. Again, I have a parameter with a default value, and this time, notice, I am actually sending this to the init method of the parent class, and everything must be fine. I run this through my mutation testing tool. I get the same surviving mutant, so again I write the same type of test, create an object, and assert what the default values of the attribute should be. And this time I get another type of exception. It's an attribute error telling me object from the motorway class does not have an attribute called speed limit. And at this point I start wondering why this is. So, I look here, everything looks cool. I look here, everything looks okay. And I traverse back to the parent class. And immediately here I notice first there's no parameter called speed limit, and then something starts to look not right. And then I look in the body of the parent init method, and nobody cares about whether or not there's a parameter called speed limit. Nobody sets an attribute called self-speed limit. So that's the problem, I don't have this. One possible fix is to, if you really need this, to just take care of it in the class under test and set the attribute. Or another possible fix is to delete everything related to this parameter. I don't bother with it. And that was actually the fix in production. Another thing which mutation testing is really good at is forcing you to look at your source code and refactor it. And places where mutation testing really shines is where you have if statements and comparisons and lots of Boolean expressions, stuff like that. The reason for this is we have many mutations in places like this. So in this example on the screen we have around 100 different mutations. Every comparison operator can lead to almost 10 different mutations. So equals here can be replaced with non-equals, with less than or greater than, less than equals, greater than equals. In Python is and is not, and also in and not in operators. So that many. Boolean and can be replaced with Boolean or. We can negate the entire Boolean expressions. Also, in the tool for Ruby, you can replace the Boolean expression with a true or false constant, and I think also you can change only parts of it, so you can replace this with true or false, and then leave the rest as is. And the Python tool doesn't do this at the moment, but it's fairly easy to add. And so this goes through mutation testing, and in something, there are surviving mutants. And when you start looking at it, you notice the pattern highlighted in red. So my thought is I can delete this and move the second block of if statements to to the right, and it becomes a little bit more clear. And then I notice another pattern that whatever the value is, I'm looking for an attribute under self-handler with the same name and do something with it. So I can refine this even further and use the get attribute function, and this becomes like this. In reality, this fits only on 4 lines instead of 10 lines, and it's much more easier to test and much more, easier to read actually, and that's a good thing. We've seen, what mutation testing can do. It forces you to write better asserts, and in my opinion, when you have a complex software under test, we not only should assert what the return values of our methods are, but we also should assert what intermediate state or side effects are produced by the functions under test. And you will all agree that it doesn't matter how much we try to write clean software, we always have these methods which do more than one thing at a time. So they do something, some calculations, return some value, and oh, by the way, I've just set this attribute on the side, just so you know. And that's what mutation testing is really helpful with. It helps you discover these things which you are not testing by mutating them, so you can write your tests better. We saw we can find some interesting bugs, and we saw that we can find places which we can refactor. And the question still stands, is my test suite good enough? And another side of this question is, how do I measure how good my test suite is? Which metric do I use to tell whether or not my test suite is good? Metrics is fairly controversial topic. I just want to mention some research that's been going on in the last few years. In 2015 at GTAC, there was one lightning talk which says, coverage is not a good metric because it doesn't give you a lot of information, so go for mutation score. Use mutation testing and measure how much of the mutants are killed. If you kill 100% of the mutants, then you're good. And then last year at GTAC, there was another researcher who basically said, well, the guys from last year, they didn't do really good research. They didn't research on many software, so we did better research, and we claim that the coverage metric like line coverage and branch coverage is still the best metric in practice. They say the problem with mutation testing is it is very expensive to compute, and in their research it gave only additional 4% of information, which the guys didn't know already compared to coverage. So they say, use coverage, don't use mutation testing. And I decided to do a small experiment and see which one of these researchers is right. So my software under test is called Pelican AB. And this is a very small library. It's a plugin for Pelican. Pelican is a static HTML generator for Python, which you can use to run your blog or your site on. And Pelican AB gives you one additional tag for the templating markup, which you can use to encode varying layout for your website. So, for example, you can change the color of links or colors of buttons, stuff like that. The way to use this software is to define the AB experiment variable in the shell and run the make command. If you run make GitHub, then the site gets rendered, everything's published directly to GitHub. The way to render several versions of your website is first start with the control version, and then name each experiment by name, and run make in a sequence like shown on the screen. And if you do this, the 3 commands, then you get the control version of your website, an experiment which is called 123, and everything about this experiment goes into a directory with the same name. The URL structure is updated, and you can point your users only to that experiment and see how they respond and stuff like that. In the version under test, we have 100% branch and line coverage of this software, and we also have a bug. There is a setting called delete output directory, which is set to true by default, and this setting isn't something the software under test controls. This lives into an external file where your website configuration goes. So stuff like your website name, your GitHub handle goes into that file as well. The bug is when that setting is set to true, Pelican will go and delete the output directory and delete all the HTML files and then starts rendering them in a clean directory. So the result of this command sequence with the settings set to true is that you have deleted your entire website and only left with the last one. And imagine now, you delete everything and type make GitHub and everything goes live. So that's a pretty good way to destroy your website. I didn't have a test which will fail if this setting is set to true. So I decided to integrate mutation testing into the project, and I wrote a few more tests to achieve 100% mutation coverage. Mind you, this is a very small library, very small plugin, and the bug was still present. So this means I don't have any test which fails when this setting is set to true. And I started thinking, okay, why I have these many tests and this bug is still present? And the answer is, you cannot discover this type of bug without looking at the external environment, and that's why we need integration tests. So I added an integration test which simulates the external environment with the settings and simulates the make command, then tries to verify what content has been rendered and whether or not it's correct, and the test immediately failed, of course. So then I said I fixed the bug, but in reality just changed this setting to false, and also added a check whether or not this is set to true, just raise an exception in my software. And now we have 100% mutation coverage, 100% branch coverage, and also we have at least one integration test. And I'm thinking, okay, I must be good then. If I have so many tests and I'm using these techniques, then possibly my software is bug-free, and of course this is not true. I've added PyLint to the project, and PyLint was immediately able to discover this bug. This is a problem with how we code the super method. Instead of passing the class name, I was using a shortcut which is self._class, and this works perfectly fine when you use the software in its intended environment, because we have only one class and self class is evaluated to that particular class's name, and everything's fine. This becomes a problem the moment you try to inherit from the class under test and create a new class and do something different with it. And then when you call the class under test init method, Python goes into a loop between the parent and the inherited class init methods. So if you want to, learn more, just head on to this PyLint pull request number, and there's a very detailed description why this is a problem. And I am guilty of using this shortcut in Python, but I've seen this in many projects online at GitHub, and I've seen this in popular software which is used by many people. So this tells me people don't have very good understanding of what self-class actually means and how it works, and that's why we keep using it in the wrong way. So to conclude the mutation versus coverage topic, this is a link to my blog describing my experiment with more details, and there are links to actual Git commits, so you can see what code was changed and how it was changed. So I think when we first start doing testing, what we look at is how much coverage we can do. So we strive to write more tests to test as much as possible of the software under test, and that's a good thing until some time. When we go to 100% coverage, we don't get any more information out of this metric, so it doesn't do any good. Then we start looking at mutation testing, and mutation testing tells us, okay, now you have some coverage and you're testing some stuff, but then there's a lot more you can test, and this is what you need to do. And we start doing mutation testing, and we get to 100% mutation coverage, and when we get to 100%, we don't get any more useful information out of that. And we also need integration tests because of the external environment. And as you see from the examples, we have different types of environments. One type of environment is the regular environment which our users will be using, and another possible type of environment is a developer just taking our software and trying to do something else with it, or build on top of it, and we have no idea what these environments will be and how people will want to use our software. So that's why we need different types of tests, and possibly we also use different types of tools to detect the problems and deal with it. And I do need more examples on the topic. I will be continue to explore this topic throughout the year. But if you have examples which you can share with me, or publish something to GitHub, please send me an email. Now I'll go to something more practical, speed of execution. So as you can imagine, mutation testing is very slow. And just to measure how slow, I've taken a real-world project from Fedora. It's called PyKickstart. It is a text parser library used by the Fedora installation program. It's a medium-sized project with a little over 100 files. I think all of these files are Python modules. They don't have many dependencies between each of them, so that's good. Each module does some checking, a few if statements. There are hardly any loops in the code, so very easy to understand actually. They read some text, then they write some text as well as an output. And this is a library which is meant to be used by other programs, so it doesn't really do anything useful on its own. The project has a fairly good test suite, over 90% coverage with a lot of tests. And the other good thing about is the files under the source directory map almost one-to-one with the files under the tests directory. So they have the same names. And the first thing I did was take Cosmic Ray, the mutation testing tool for Python, and told it, okay, so here's the source directory, which means load everything into memory you can find under this directory in terms of modules, produce all the possible mutations you can produce on these modules, and then here is the test directory. Use the test runner to discover all possible cases you can discover and just start running. And I let this run on my computer. That took over 6 days. Then I became smarter and wrote a small script to go through the source directory, take only one file, load this into Cosmic Ray, which means produce mutations, but only for that module. Don't bother about the rest of the software, only that module. And oh, by the way, here is only one file in the test directory which contains your test, so use only that for testing and not everything else. And that was faster. I've also added an option called fail fast, which means whenever one of the tests fails, we know that there was a failure and we'll kill the mutant, so don't bother to execute the rest of the cases. This is an option for the test runner. And I did some refactorings, like stuff like if length of string is greater than 0, I've replaced this with only if string. And this helped me save about 1,000 mutations, which were very obvious things. And I let this run. The execution time was now a little over 6 hours. And this is a 20 times more improvement in speed of execution, but still quite slow for any practical purposes, I may say. So the way to use mutation testing at the moment, in my opinion, is if you're testing a very small library or a very small project, then you can go full on into CI and just tell, okay, this is my command line to schedule my mutation testing jobs, and let this run for 10, 15, 20 minutes, and that should be fine. If your project is anything bigger than 200 lines, this is not going to work very well. But what you can do is create a commit hook or a pull request hook, which examines the payload. And first thing you can do is schedule mutation testing only against the files which have been modified by that particular commit or that pull request. And that should be faster. Next thing you can do, depending on the tooling, is go down from the module level to the class name and to the method name which has been modified. The Python tool doesn't know anything about classes and modules. It only knows, doesn't know anything about classes and methods, sorry. It only knows about modules. So regardless if you have 1 class or 1,000 classes in one module, Python loads the entire module and starts doing mutations against everything. On the other hand, the Ruby tool knows about classes and methods, I think, and you can tell, test only that particular stuff. And you can try and go even further because this is a pull request or commit hook. You have access to the actual diff, and you can apply this to the source under test. And assuming you've tested everything before and it's fine, then you can schedule mutations only against the lines which were changed. So you can do this, and it's not really impractical to do this. Another thing you can do is go into parallel. Again, depending on the tools, the Python tool is built around Celery, so you can very easily hook this to some messaging backend like RabbitMQ and schedule hundreds and thousands of messages and let your infrastructure deploy Docker instances or virtual machines in the cloud and just run your tests in parallel, just get back the results. And you can do this if you have a lot of money, of course. Here is a list of some mutation testing tools. I have been using only the first two. I mostly use Python, and I contribute to Cosmic Ray for Python. And I've used Mutant for Ruby, but not very actively at the moment. And the names to the right are GitHub repositories. Okay, so as far as I know, the tools on the top are based on the abstract syntax tree of the language, and they are language specific. So whatever you want to do in the tool, it works on ASTs. It modifies the nodes of the AST. One thing I like to do is look at the other tools and see what they're doing, especially in terms of mutation operators, and try to bring these to Python. So if you want to actively use mutation testing, I really advise you to look at tools for other languages and see how they work and how they are doing, because many of the tools are very new, they're not very mature. And on the bottom, this is another tool for mutation testing called the Mule project, which Alex Denisov will be presenting later today. So I'll definitely be checking this out. This is an LLVM-based tool, so it should work for several different languages. If you are into mutation testing, also check this out. And now, before I can go further, I can take some questions from the audience, if you like. Okay, go.
If we have a zombie that had 1%, 100% coverage, does it mean that our code coverage metrics was wrong at the first place? For example, if we have some lines of code hidden inside of our language, and we miss them from the start.
Okay, so the question is, if we have a zombie but we have 100% code coverage, does it mean that coverage was wrong?
At the first place.
Yeah.
The lines are hidden within the language itself.
Yeah. Okay. So it doesn't mean coverage was wrong. Like, I mean, it doesn't mean the metric, the measurement was wrong. It was probably correct. There are other problems with coverage. Like, for example, if you have one line with lots of with a long Boolean expression, then it still gets covered regardless of how much of that expression is evaluated. So you may be evaluating only the first part of the expression and still cover that line, but the next 10 parts of the Boolean expression are not evaluated.
It's not a one line, it's multiple lines.
Yeah. Well, the way to count, these cases is you should take this up to the tools, to the authors of tools who do coverage. But there are many publications online with respect to problems in coverage and why it's not really a good metric, why you shouldn't use coverage. And really, for me, coverage is a vanity metric. It really tells you how much of the lines you've covered, but nothing more. It doesn't tell you anything more. And if you have a zombie on a line which was covered, this simply means you might have executed this line, but probably you didn't assert on some condition, or you asserted on one condition and you needed to assert on two conditions.
Well, I have a comment to that.
Okay.
Basically, this is a difference between line coverage, statement coverage, and branch coverage.
Yes,
If you
yes.
have 100% branch coverage, then it's unlikely that you will have 100% coverage and have zombies. But most of the tools count only line coverage, and very few count even statement coverage, not to mention branch coverage.
Okay, we have a question there.
Yes, so this works really well with primitive operations that we change, less than, greater than, plus, plus, into plus two. What if you're not using primitives for your business logic? What if you're using a library, especially in JavaScript, but I don't know about Ruby, that does all your conditions for you with functions?
Okay, so the question is, what if we don't use primitives, we use some library for the business logic? How does mutation testing come into play? Well, this is very dependent on the tools that you use. So, for example, the Python tool until recently, it was very poor on mutation operators because it's a new tool and not many people use it. On the other hand, the Ruby tool called Mutant, I think this is one of the best tools currently in existence. And it has tons of mutation operators, tons of conditions. It understands, because it's used by people who work on commercial software, they get paid to actually write test suites for commercial software, and they support the tool for that reason. About JavaScript, I don't really have no idea. I don't use JavaScript, but really the take here is you need to know your tools very well, and you need to know the software very well. And that's when you can decide whether or not that's going to be useful. Now, maybe in your case, you might write a plugin or an extension to the tool and produce the mutation based on the functions in that particular library. Okay? Question here.
So thank you for your talk. Academia claims that the biggest problem of mutation testing is equivalent mutants. Can you say something about them? How often do you see them in production, or is it something that you struggle with in practice?
Okay, so the question was about equivalent mutants. Equivalent mutants are things like which change the code but don't really change behavior in any practical way. So, for example, we may have a less than operator, which in practice is equivalent to less than or equal, if we, depending on the values we accept in the application. And I don't have any concrete measure about this in practice, but I think about 10 or 15% of the time I see equivalent mutants. Equivalent mutants because the behavior doesn't change, but the syntax changes, but the behavior doesn't change. The test suite doesn't fail, and we cannot kill them, and they just stay as is. In the projects I use mutation testing for, I usually have some threshold, like about 10% or something like that, and if the mutant score is above a certain line, then I say we're good, and then the CI system goes green. And if we drop under that line, then we go red and inspect what's happening. And that threshold is based on how many equivalent mutants I have. So I try to get some idea about that and then go from there. I've talked to other people who do mutation testing and have been doing mutation tests for a long time. And this is a problem, but still the benefits you get from asserting on all those different conditions and looking at your code base and understanding the software much more better, which is a result of mutation testing, it just, the benefit is greater than having to deal with equivalent mutants.
Thank you.
Okay. Okay, more questions or no questions? We have 2 minutes, so if there are no more questions, I'll just show you this very quickly. I have started to document my findings about mutation testing. So first of all, I don't forget them, and some of them make really good examples. This is available on Read the Docs, and it's also available on GitHub if you'd like to contribute. And since the last week, we have also Chinese translation for this. And I'll skip the trivial examples and show you the last one. So we have this in Python. It's fairly common to have methods for equality, which compare two objects by comparing that all of the attributes are equal. So in this example, we have a class called sandwich, and you can modify the meat of your sandwich and the bread type of your sandwich. And we say that two sandwiches are equal if meat and bread attributes are equal. And that's about it. We have a safety check here. If the other object is none, then return false. And the not equals method is just a negation of the equals. And the way to test this with mutation testing is like so. So we create two test objects, sandwich 1 and sandwich 2. By default, all of their attributes have a value of empty string, which is not shown on the screen. And first thing we do is test for equality. They should be equal because everything is an empty string inside these objects. And we also assert that the two objects are not, when compared for non-equality, it returns false. And that takes care of half of the testing. Then we test the safety check compared to none and expect to not be equal. And then comes the fun part, the way to, so this starts changing into different comparison operators, and the way to test is like this. So we need to modify only one of the attributes at one of the test object and leave the rest of the attributes and the other object unchanged. And we need to do this for every single attribute. So when all the attributes are of the same type, you just do this. And if they're not of the same type, you can do grouping or something like that to, to modify this block. So when the time's up, so thank you very much.